In the early days of multi-cylinder water-cooled engines, each cylinder was bolted down separately to the crankcase, and each one therefore needed a jacket around it to contain the water. This is a photo of the engine I copied, kept in storage at the Science Museum facility near Swindon, now in a very dilapidated state. It's been there for the best part of 100 years. One of the cylinders has been sectioned at some point in its long history, giving us a valuable but somewhat restricted look inside. The red arrows show some of the water space, and the jacketed water spaces were interconnected by pipework and fed by a pump at the rear end, which you can't actually see. This one is an earlier French engine, the famous Antoinette, that used the same process, sometimes in brass, as here. Very pretty, I think. There were two ways of making these jackets, one by a process called electroforming, which is what I'm going to be talking about, and the other by the somewhat simpler method of encasing the cylinder in a more or less round tube, sealed at both ends by various rubber rings. The well-known Green Engine Company used this system, but it was very prone to leakage. In those days they only had natural latex rubber, which rapidly deteriorates, as we all know. Here is my half-scale replica with the cylinders all ready for their jackets. The electroforming process was well known to Victorian sculptors for making complex shapes, as well as jewellers, dentists and engineers. It's still used to make complicated thin-walled objects in copper, nickel, chromium, sometimes gold and silver, and is really just an extension of electroplating, but with the difference that the substrate, the thing you plate onto, is removed afterwards, leaving a thin shell of the new metal. The downside is that it's quite difficult to do, and much can go wrong in a home workshop, especially if you lack experience. I'd been given a basic recipe by a model engineer friend many years ago and used it to make some simple inlet pipes for another engine, but I lacked knowledge and at the time couldn't find much on the internet to guide me. Quite a bit for jewellers, but nothing for the amateur engineer wishing to work accurately to drawings. In this photo you can see the result. I'd made some of them, with 3 more to go. So, what are we going to plate onto in this case? Going back to the previous photo, you can see each cylinder has a number of brass flanges and a large brass ring around the middle. The jacket will be bonded to these, but we have to fill up the space between them where the coolant will be with something else, which can be plated but then removed. The best material is a low melting point alloy that can be cast around the cylinder and lie flush with these various flanges. Once plating is complete, we'll melt out this alloy, leaving the copper shell behind, but attached firmly to those flanges. If done correctly, the plating will adhere strongly to the flanges to make a watertight joint. So the first thing to do was to make a pattern to represent the final shape of the jacket. I used PVC for this, making it up from chunks, plus a large amount of epoxy filler. As these two materials are different colours, I painted the whole thing black so that I could easily see that the various curves blended into one another properly. Much easier to do if it's all one colour. The pattern was then used to make a mould into which the alloy would be cast. And here I made a mistake. I should really have used silicone rubber for this mould rather than plaster. It would have probably remained intact for all 8 castings and given a much better surface, whereas the plaster cracked with the heat and for some unknown reason gave the castings a very rough orange peely sort of finish, which needed a lot of work. A false economy. Luckily I'd allowed for a bit of sanding down, but it all took more time. The alloy I chose was a tin bismuth one having 0 shrinkage. It has the added advantage in being non-toxic, containing no lead or cadmium. But it's expensive, so I got enough for just a couple of castings with the aim of reusing it, and even collected all the filings. You could use wax for this job, but it's very difficult to cast accurately and shrinks a lot during solidification. And then you've got to make it electrically conductive by painting it with something that contains copper powder or the like, so that it works properly in the electrolyte and attracts the copper ions towards it. A metal alloy is much better for engineering work. You may be wondering why the flanges were made of brass. Well, the reason is that plating directly to steel is difficult without either the use of cyanide to prepare the surface or a strike coat of nickel first. Getting a bit complicated, not to say dangerous, I thought, in a small home workshop. So I opted to silver solder thin brass rings onto the steel surface, to which the copper would then attach easily, I hoped. Another thing you may notice is that the cylinder has been painted with a thick layer of heat-proof epoxy to prevent contact with cooling water. An unnecessary step as it turned out, because I later decided to use waterless glycol coolant, which wouldn't corrode the steel. If I were to do it all over again, I would definitely leave off that paint and give the whole thing a nickel plate first. Here are the various stages. Bare cylinder on the left, then the pattern, then a casting next to one of the moulds. I had to make several of these, although some were used twice. The next picture shows the alloy being melted on a small stove in an old ladle. Ignore the small mould boxes at the front, these were for something else. The next job, having got the surface as smooth and as accurate as possible, is to clean it thoroughly, especially the areas that will be permanently plated, i.e. the flanges. This involves the use of lots of water and soap with a final rinse in distilled water. There's no need for any chemicals, certainly not organic cleaners, that tend to leave micro deposits. The test for a truly clean surface is the water break test. Providing water leaves a continuous film all over the surface without dividing into droplets, you can say it's clean. You basically just hold it under the tap and look at it, and if you get a continuous film of water, you know it's clean. Except it's not the tap, it's got to be distilled at that stage. But then plating must begin immediately, because brass surfaces are liable to start oxidizing in the air almost immediately. To prevent water and then electrolyte getting into the interior of the cylinder, I blocked up all holes with soft silicone bungs and the main bore with a large plastic plug attached to a mounting plate. I took the added precaution of spraying wax oil all over the insides, then sealed up the lower half completely with duct tape. Now here I need to jump ahead a bit to mention my first experience of trying to melt out the white metal following plating. This was easily done in the domestic oven, but by having a careful record of weight at every stage, I calculated that about 5% of the alloy had remained stuck inside as a film all over the copper, rather like soft solder might. This didn't really matter, except for the waste of a valuable material. So I sat down to think how to prevent that happening. I had the idea that there might be something I could paint on the alloy before plating that would work as a non-stick surface, but it would have to be electrically conductive. Something like a carbon paste, maybe. So, what could be used? I discovered I'd got the ideal stuff, as it happened, in a cupboard, and it's called Zeebrite in a little yellow tube. And for those not familiar with this, it was sold years ago as a waxy blackening compound for cast iron stoves and fire surrounds. You can just rub it on with a finger, and it contains a lot of carbon, probably lamp black, soot in other words, some wax and some sort of solvent to liquefy it a little bit, but it's just a paste. So I did that, and the remaining jackets yielded just about all the white metal with no trouble. Lovely old-fashioned solution. That's why this one in the photograph is black, and it's now ready to go into the plating bath. The electrolyte is a solution of 10% sulfuric acid, copper sulfate, a tiny bit of non-iodized salt, and some special chemicals bought from one of the suppliers of plating kits for home use. You don't need much of these, but they do help to give a more uniform surface. They're known as levelers and brighteners, and I really don't know how they work. They're organic copper compounds. Then you make up the bulk with distilled water. The process works at room temperature and is very slow. I was going to need a couple of days to get this done. Now it's normal to tumble or turn the whole job, the cathode, in all three axes, so that every part of its surface gets equal exposure to the anodes, which are arranged around the edge of the bowl. Well, I couldn't do this because the job was just too big and heavy, and I saw no easy way of turning it while maintaining its electrical supply. So I relied on moving the solution around with bubbles from an aquarium aerator, which you can see in the photograph. Plus, of course, a lot of hoping for the best. There's quite a bit of that in my workshop. Often you just have to try things out and see if they work. The anodes were pieces of copper sheet, ordinary stuff, and not at all the spec recommended by the experts, which, needless to say, is virtually unobtainable in small quantities and probably very expensive. Here is the bath. I used only 10 litres of water altogether. The anodes were enclosed in filter bags made of acid-resistant polypropylene. I found that on the internet somewhere. It's proper filter material, filtering down to 10 microns. And it's very important for collecting the mass of sludge that forms around them and stop it getting onto the job. I used a small DC power pack and calculated that about 2 to 3 amps would be suitable. And you get this figure by working out the surface area of the job, that's to say the cathode, and multiplying that by somewhere between 50 and 75 milliamps per square inch. And in my case the area was 42 square inches. The controller then provides an appropriate voltage. In this case I think it was about 2 volts. The lower the setting, the slower the plating, but I found I got a much smoother surface. If you go too fast, the surface will be covered in tiny nodules, which then of course have to be sandpapered off. Great nuisance. Altogether, each one needed about 48 hours to acquire the design thickness of about 0.5 millimetre. Of course, it becomes very tempting to take the thing out after a few hours plating and have a close look at it. With hindsight, I'm not sure this is a good idea because while out of the bath, the copper will immediately start to oxidize, and that may well inhibit the adhesion of a subsequent layer. I got the idea that the process is rather like painting. For the best finish, you rub down between coats, getting rid of all the imperfections. Then with luck, the final coat will be free of blemishes. But this technique may well be wrong. I simply don't know. These pictures show some mystery defects, small scars and pits that simply appeared, perhaps caused by bits of muck settling on the surface or the dead flies that I found, and quickly getting trapped by copper being deposited around them. So I did sandpaper them out after about 24 hours and then carried on with a further day. Then a final sanding, followed by polishing, resulted in a clean finish that seemed acceptable. I got some idea of the thickness of the plating from my detailed record of weight. The change in weight during plating could be used to calculate the mean thickness, which was a guide but told nothing about the unavoidable variations. Generally, I knew that sharply curved areas like corners and fillets around the stub pipes would get a heavier deposit relative to broad, flatter areas, and this seemed like no bad thing. But those broad areas, like the top and sides, were unsupported by anything inside, so I went well beyond the point when the mean thickness worked out at 0.5 millimetre, aiming at about 0.7 instead. I might know more after the first one had had its substrate removed, and then see how much those areas responded to being gently squeezed. Copper deposited in this way, contrary to what you might think, behaves like normal elastic sheet material, not at all brittle like a casting and not like soft annealed copper. It's quite tough and springy. However, there is uncertainty about adhesion between successive coats. I discovered later that unless you plan to heat the article for something like silver soldering, adhesion is good enough. But if you plan to heat it up to brazing temperature, the top layer of plate may well blister away from lower layers, which would be disastrous. One trick I learned later was that the power should be turned on just before the job is immersed in the tank. If this isn't done, deposition will start anyway without the current, but that very first film of copper will not be firmly attached. So you need to have the current flowing right from the very beginning. Melting out the white metal was easy enough. As I mentioned before, I did it in the oven indoors. Although each one took the best part of an hour, the oven temperature set at 150. I fixed the job on a light steel frame upside down and tilted so that metal would run into a tray underneath. I had ground off the two copper caps that had formed over the ends of the stubs, which could now be called pipes. Each one was done separately, as I mentioned before, as I had a limited amount of alloy and needed to learn the process as I went along. An early test for air tightness revealed that all was well at the joints, while tapping with the fingers all around suggested sufficient strength and thickness. There'd be no significant pressure caused by the coolant in use, as the system would be open to atmosphere, but there would be stress set up by unequal expansion because you've got copper bonded to steel, and vibration, of course, when the engine was running. So I pressure tested each one with air up to about 10 psi, and they were all okay. In this final photograph you see the induction pipe work. I had to make this all by the same method. Looking at the full-size engine, this pipe work was clearly very, very thin. It was heavily dented, and I couldn't see any ruckles on the inside of those sharp bends, which led me to think that it must have been electroformed rather than hydraulically bent. So I did the same, and the tubing I used, of course, was a non-standard size. It was I think about 16.5 mil OD. I mean, impossible to find, so I had to make something. And the electroforming was easy enough because I'd had some practice by then, but the mold making and the definition of the geometry was very hard to do. I'm not going to go into all of that now. I have written about it in the Model Engineer magazine in the past, so it's all out there if anybody's really interested, and if they want to contact me, I'm happily point them in that direction. The various individual parts were soldered up, partly with silver solder and partly with soft solder. The whole thing was a mess, but I managed to get there in the end. The engine now has had about nearly 5 hours of run time, and it's going beautifully, I must say. All 8 cylinders firing, and not much oil being spewed out, no smoke, and it runs about 2000 RPM maximum or a little more. Idles at about 900, and we did a spring balance thrust test on it some time ago and registered about 20 kilograms at 2000. So I'm pretty pleased with it, and now of course somebody needs to build a half-sized biplane, perhaps a Howard Wright biplane, and replicate Sir Tom's historic flights. Well, I hope you've enjoyed this video and got something out of it. Thanks for watching, and do have a look at the others on my channel. Feel free to ask questions and I'll do my best to answer them.